Welcome back to another episode of Miss Bioscience. Bipedalism, the ability to walk on two legs, has played a crucial role in the success and adaptation of our species. Understanding how and why bipedalism evolved in humans requires an exploration of the anatomical changes, the fossil record, environmental factors, and potential advantages that walking upright offered to our early ancestors. Let's see if we can accomplish that in about 5 minutes. We'll start with a series of significant anatomical changes that took place in order to walk bipedally. One of the most critical adaptations was the restructuring of the pelvis. In bipedal hominins, the pelvis became shorter and broader, which helped stabilize the trunk while walking. The femur, or thigh bone, also underwent changes, becoming angled inward toward the knee in what is known as the Q angle. This adaptation allows the foot to be placed directly under the center of gravity during walking, which improves our balance. In order to accommodate birth, the female pelvis is typically wider, and thus female skeletons can demonstrate a larger Q angle than male counterparts. The foot itself has also evolved to support bipedalism, as we'll see in the fossil record. Humans have developed an arched foot, which acts as a shock absorber and provides the necessary spring for walking. The big toe became aligned with other toes, a departure from the grasping feet that we've seen in other primates. Additionally, the spine developed an S-shaped curve, which helps to maintain balance and absorb shock as the body moves. The arms and hands of bipedal hominins have also changed. As our ancestors relied less on their upper limbs for locomotion, their arms became shorter relative to their legs. The hands became more specialized for manipulation and tool use rather than for locomotion or climbing. Evidence of bipedalism can be found in the fossil record over millions of years, with the earliest known bipedal hominin dating back to around 7 million years ago. One of the earliest known potential bipeds is Sahelanthropus chidensis, discovered in Chad. This species had a foramen magnum, the hole in the skull where the spinal cord passes through, positioned more towards the base of the skull, suggesting an upright posture. Another early hominin, Auroran tuganensis, which lived around 6 million years ago in what is now known as Kenya, also shows evidence of bipedalism, with femurs adapted for walking on two legs. Otherwise, little is known about these species. Living approximately 2 to 4 million years ago, Australopithecus afarensis, famously represented by the fossil Lucy, demonstrated an interesting mix of human and ape-like traits. It's a much better understood species because more than 300 individuals have been discovered and studied. They had a pelvis and leg bones adapted for bipedal walking, including a big toe that was aligned rather than opposable, although they still retain some features for tree climbing, such as elongated arms and fingers. The anatomy of these early hominins indicates that bipedalism was well established by this time, even if they were not as efficient walkers as modern humans. When the genus Homo arrived on the scene about 2 million years ago, we saw a loss of tree climbing traits. Arms became shorter, and the lower body became more efficient in bipedal locomotion. So efficient that Homo erectus was the first hominid species to leave Africa. Fossilized remains have been found in Africa and Asia, but it is unknown if they ever made it to Europe. So why did natural selection begin to favor bipedalism? One prevalent hypothesis suggests that bipedalism evolved as the response to a transition from dense forests to more open savannas in Africa. As the climate became drier and forests receded, our ancestors were increasingly exposed to open landscapes where food and resources were more widely dispersed. Bipedalism would have provided several advantages in this new environment. Walking on two legs is also more energy efficient than quadrupedalism, especially over long distances. This efficiency would have been beneficial for early hominins who needed to travel between patches of food and water. Bipedalism also frees the hands, allowing early hominins to carry food, tools, and infants. This capability would have been particularly advantageous in an environment where resources were spread out and needed to be transported. Another theory suggests that bipedalism evolved as a way to regulate body temperature. Standing upright reduces the amount of direct sunlight exposure to the body, particularly on the back, while increasing exposure to cooling breezes. This would have been an important adaptation in the hot and arid environments of the African savanna. To sum it all up, the transition to walking on two legs involved significant changes in the skeleton, particularly in the pelvis, legs, and feet. Environmental changes, such as the spread of savannahs, likely provided the initial impetus for bipedalism. by making energy-efficient locomotion and the ability to carry more objects advantageous. Understanding the origins of bipedalism not only sheds light on our physical evolution, but also on the unique adaptations that have made humans one of the most successful species on Earth.